Hello everyone, we are Group 18 and today we are excited to present our term paper on DINOv2, Learning Robust Visual Features Without Supervision. This work explores how self-supervised learning can be scaled to produce powerful, general-purpose visual models without relying on label data or text supervision. To start, this work aims to create a single vision encoder that works out of the box for both image level tasks like classification and pixel level tasks like segmentation without needing any labels or fine tuning. The authors trained a massive 1 billion parameter vision transformer called VITG using 142 million curated images and a refined self supervised learning method. What's powerful is that this big model is distilled into smaller versions, VITS, B, and L, so others can reuse these features easily. Even without any text, these frozen features outperform or match models like Clip that rely on captions. It's a big step towards making vision models more accessible, robust, and environmentally sustainable. We have already seen the success of foundation models in NLP, like GPT or BERT, which produce task agnostic features that work out of the box. The same idea is now being applied to vision. A single encoder that works across many visual tasks simplifies pipelines dramatically. For example, instead of training a new model for classification and another for segmentation, you just use the same encoder. And self-supervised learning helps scale these models without relying on manually labeled data or captions. So there's no caption bias and it's much more scalable. So what sets DINOv2 apart? First, the authors improve the self-supervised training recipe by tuning hyperparameters, adding regularizers like Colio, and optimizing loss functions. Second, they scale up training with VITG over a billion parameters and then distill this into smaller VITs to make the model more usable. Third, instead of using noisy, uncurated data like past work, they build a high quality dataset of 142 million images using clustering based curation. And finally, they make training efficient with technical tricks like flash attention and sequence packing, which reduce memory and speed up training, making it practical to scale. The core objective here is to prove that you can build a strong, ready to use vision model using only pictures, no labels, no text, no captions. The idea is to train a large VIT on a clean, diverse patch of images and produce a model that works across many tasks like classification, segmentation, depth estimation, and more. And they succeed. The resulting DINOv2 models not only match but often beat text supervised models like Clip. This shows that with enough data and the right training recipe, self supervised learning can truly stand on its own and scale like NLP models have. This slide summarizes 4 main lines of work in self supervised learning for vision and where they fall short, especially in the context of DINOv2 tries to solve. First, intra-image pretest tasks like patch prediction or in painting helps model learn from single images, but they usually need supervised fine-tuning to be useful. Frozen features remain weak. Next, discriminative SSL methods like instance contrast and Dino try to bring similar images close together in feature space. They work well on curated datasets but often struggle to scale. Quality drops when the data gets larger or noisier. The third, scaling SSL, has trained large models like VITL using uncurated web data, but this data is often noisy and biased, so models still need task-specific fine-tuning. Finally, we have automatic data curation, which is relatively new in vision. Prior work rarely curated data at this scale. DINOv2 introduces a clustering-based pipeline inspired by NLP to create a high-quality, diverse dataset that's central to its success. This figure shows the first 3 PCA components of DINOv2 patch level features, visualized as RGB colors. Each row has similar looking images, and what's impressive is that the model aligns key parts like wings, heads, or wheels across different styles, poses, and even object types. This proves that DINOv2 learns consistent, semantically meaningful features at the pixel level without any labels or segmentation supervision. This figure shows how DINOv2 scales across 8 vision tasks at model sizing phases. The blue line represents DINOv2, clearly outperforming previous self-supervised models, orange, and even matching or surpassing weakly supervised models, pink, on most benchmarks. Notably, it achieves strong results in fine-grained tasks like segmentation, instant retrieval, and video understanding, despite using no labels or caption. This highlights DINOv2 ability to deliver robust, general purpose features at scale.
begin with next section, that is data processing. The DINOv2 team found that existing self-supervised models struggled when scaling beyond ImageNet 1K because they often relied on uncurated, noisy web images. This leads to poor generalization and representation quality. To solve this, they introduced a novel automated data curation pipeline, aiming to capture the benefits of scale and diversity without sacrificing quality. The result is called LVD 142 million high quality and diverse images. Here's how it works in detail. First, they gather a few trusted curated datasets, ImageNet 22K, Google Landmarks, and fine grained classification datasets. These serve as the high quality reference set. Then, from a large web crawl of around 1.2 billion raw images, they extract image URLs from tags across web pages and download them. These raw images go through several filters such as NSFW removal, face blurring, PCA hash deduplication, and safety checks. The next is the core step, that is embedding plus retrieval. All images curated and uncurated are passed through a self-supervised VIT model to generate feature embedding. Then, using cosine similarity, the system retrieves visually similar images from the uncurated pool for each curated image. This step ensures visual diversity while preserving the core semantics. To maintain efficiency, they use FAIS, that is Facebook Similarity Search Library, with GPU acceleration, product quantization, and k-means clustering to scale this process. This process is fully unsupervised. No labels, caption, or external metadata are required, just the structure of visually similar itself. So the final LVD 142 million dataset balances scale and cleanness, outperforming both ImageNet 22K and raw uncurated dataset in downstream tasks, including transfer learning and generalization. Next, moving on to the discriminative self-supervised method, we focus on how DINOv2 actually learns from the data. The key idea here is to combine two complementary objectives. DINO, image level loss, that is, it trains the model to match global representation between two views or crops of the same image. It uses a teacher student model. The teacher is an EMA, that is exponential moving average or of the student weights. And the second key idea here is IBOT patch level loss. That uses masked image modeling where the paths of the image are hidden from the student and the student is trained to predict patch level representation from the teacher. This captures fine grained structure. They further refine the setup by untangling the heads for these losses using separate MLPs for Dino and iBot rather than sharing them, which improves performance at scale. To stabilize training, they introduce SkinCon knob centering from SWAV, which avoids dominance of frequent patterns in the prototype space. And the second, they use regularizer, which encourages a more uniform feature space by penalizing clustering of sample. Here, here is the formula briefly for Colio regularizer. It computes the log of the minimum pairwise distances in the batch and promotes spread out embedding. This is important for retrieval and transfer learning. Another small but impactful trick, a short high resolution phase is added at the end, by which images are trained at 518 cross 518 pixels instead of the usual 224. This drastically improves performance on dense tasks like segmentation and depth without much computation overhead. Altogether, these design choices makes the DINOv2 framework highly robust, stable at scale, and versatile across both image level and pixel level tasks. So, next in the efficient implementation section, the author tackles one of the biggest challenges, scaling to a billion parameter models while keeping training efficient and reproducible. The backbone here is custom VITG model with 1.1 billion parameter. So several engineering optimizations are essential. Let's walk through key improvement. First, talking about flash attention, a highly optimized attention mechanism that computes self-attention in a memory efficient and fused manner. It helps reduce overhead on 800 GPUs and is customized here to support a wider range of hardware and dimensions. Second, sequence packing. In standard Dino training, images are processed in multiple crop sizes, for example 98 and 224 resolution. Normally, these require separate forward passes, but with sequence packing, they combine all crops into a single long token sequence and use a block diagonal mask to restrict cross attention. This gives a significant speed up. Next is the efficient stochastic depth. Instead of applying dropout to outputs, this skips entire residual blocks during training. It saves compute directly and helps scale up high drop rates up to 40%. Next is the fully shared data parallel FSDP. This breaks the model and optimizer states across GPUs, so one is no longer limited by the memory of a single GPU. FSDP also uses float 16 for communication, reducing bandwidth cost by around 50%. And finally, model distillation. For smaller VIT models like VITL, they don't train from scratch. Instead, they distill knowledge from the VIT-G teacher. The training loop remains mostly the same, but the teacher is frozen and the student mimics its outputs. Interestingly, even distilled VITL outperforms the same model trained from scratch across 12 benchmarks. All the codes and models are released under APAC 2.0, making these improvements directly usable in other version applications.
Welcome to the evolution study section. Here we break down how different training choices impacted performance on DINOv2. So let us start with recipe upgrade payoff. So first stacking 11 training tweaks on the top of the iBoard baseline gave a big toast here. On ImageNet 1K, KNN accuracy performance jumped from 72.9 to 82. That's a 9-point gain. The biggest contributor were the Colulos, which added plus 2.3 points and increases batch size which gives a plus 1.2. This shows how small technical adjustment can significantly add up when combined. So next point is clean data beats quantity alone. So data quantity matters more than the quantity. The VITG model trained on the curated LVD 142M dataset performed better than the same model trained on the 142 million uncurated web images on the Oxford M dataset. The curated version improved map by plus 10 points, so better data gives better results, as we all know. So sorry, I move forward. So next point is loss roles are distinct. Different loss functions serve different purposes. The Colu regularize improved retrieval performance by plus 8 map on Oxford map. Meanwhile, the iBot map patch sizes loss improved segmentation on ADE 20K by plus 3 MIOU. Both losses bring value but for different type of task. So now it's time to move on next slide. So bigger model loves bigger model is the next point here. So as model increases, so does the need for large and rich data increases. Larger models like VITG benefited significantly from the LVD 142M dataset compared to the ImageNet 22K. So this tells to unlock the potential of higher architectures as also need bigger and cleaner dataset. Okay, so next point is distillation is free gain. So distillation turned out to be a huge win. A smaller VITL model distilled from a VITG outperformed the same model trained from scratch across all 12 benchmarks. This means we can get the performance of large model in smaller, faster model for free compute wise. So next slide is, so here is the table. So in this table, this is a iBot versus DINOv2 tweak table. So here is a layer by layer view. Each row shows a tweak added to the iBot baseline. Colium, warm-up schedules, batch size, all contributed meaningful gains are here. Some changes like layer scale, reduced linear accuracy, but perform training stability, showing a trade-off. The final DINOv2 model combines the best of these for optimal results. So it's all about this table. So next, here is also table number 2 from the ablation study section. So this is a table for ablation of the source of pre-training data. So the table compares performance across dataset. LVD142 outperformed uncurated data across all benchmarks and was competitive with ImageNet 22K, even better on several tasks. Carefully curated diverse data leads to better, more general visual features. So it's all about this table. So now we move forward. So this is a figure uh, which shows the model scale versus data scale. So this figure shows how scaling models with high quality data matters across benchmarks like cars, Food 101 and Oxford H. VITG model trained on LVD 142M consistently beat the same model trained on ImageNet 22K. More data, better models gives better results, as we already know that. So it's all about this figure. So next we move forward. So here we discuss about colio and MIM loss effects. So here we isolate the effect of colio and MIM losses. Removing colio drops Oxford M retrieval map from 63.9 to 55.6. Removing MIM reduced segmentation MIOU by nearly 3 points. Together, these ablation confirms that both losses are essential for different type of tasks. So we will discuss in next slide here in summarized way. To sum up colio loss, improve retrieval, MIM improve segmentation, and each training change contribute differently. All models were trained for equal steps, and results uses simple linear props, showing the direct effect of each component clearly. So, so here we can see effectiveness of knowledge distillation. So this is a radar chart that shows performance across 12 benchmarks. The VITL distilled from VITG consistently outperforms the same VITL trained from scratch, sometimes even surprising the teacher. Distillation makes models both smaller and smarter. It's all about this figure. So next is this is the here is the role of resolution. So role of resolution, but training cost is high. So model trained entirely at 416 pixel to do best, but training first at 224 and finishing at 416 give similar performance at for lower cost. That's why DINOv2 includes a short high res finisher stage at the end here. So let's now I can summarize the whole ablation study in few points. So ablation study in DINOv2 teaches a lot: better recipes, clean data, task specific losses, and model scalings, efficient training tricks. And it also teaches knowledge distillation. All play key roles. Combined, they enable DINOv2 to deliver state-of-the-art, self-surprised performance across image pixel and instance level tasks. So it's all about the ablation study parts. So thank you.
So hello everyone, I am Shafiq. In this part of the presentation, we will explore the result presented in the DINOv2 paper. So the goal of the demonstration of the results is to show that DINOv2's self-supervised features outperforms the current state of the art in SSL and are competitive with or surpass the WSL features on many tasks. On many tasks. When coming to the baseline SSL and WSL models that are publicly available. So SSL models such as MAE, Dino, iBot are compared with the DINOv2, and WSL models such as Clip, OpenClip, EVA Clip, Swag are compared with DINOv2. Now, to assess the quality of the learned features, the authors used three evaluation methods: linear probing, few-shot learning, and fine-tuning. Now, these tests are run across the standard vision tasks such as classification, semantic segmentation, depth estimation, and image retrieval. So here is the results of linear evaluation on ImageNet 1K frozen pre-trained features. Here top one accuracy on the validation set for publicly available models trained on public or private data with or without text supervision are reported here. So in the top table you can see the weakly supervised models such as Clip, Swag, OpenClip, and EvaClip, and the architecture used are VITL, H, and G. So the data that have been used to train these models are also listed here, and you can see there are two strategies to evaluate the models. One, it was evaluated using KNN, and also it was evaluated using the linear classification. So here you can see the DINOv2 basically outperforms any of these methods such as self-supervised or weakly supervised previous methods. So you can see the previous version of Dino had accuracy of 79.2, and the current version or version 2 has accuracy of 86.5 on the VITG architecture. So it's quite an improvement over the previous generation of Dino or any generation of any version of SSL or WSL methods. Now these are some other results on image and video classification. So on image classification, OpenClip, MAE, Dino, and iBot are compared with this DINOv2 with different various VIT architectures, and for video classification different data sets are used to compare the video classification results using the same linear evaluation method. And here you can see it has an accuracy of 78.4 on the K400 dataset and 91.2 on the UCF 101 dataset and 38.3 on SSV2 dataset, which doesn't outperforms the other SOTA models. The iBot actually has better performance than our DINOv2. Now the key takeaway is that DINOv2 has an accuracy of 82.8 using only linear probing method, that is without fine tuning, and this is better than previous SSL models such as Dino, iBot, and the MAE model. And the insight here we can take away is that DINOv2 produces highly linearly separable features, which is a hallmark of strong representation learning. Now coming to domain generalization results. Results, here also DINOv2 outperforms the SOTA models such as iBot, MAE, and Dino. So it cannot outperform the OpenClip model, which has an accuracy of 87.8. So it has an IMR score of 87.8, IMC score of 28.2, and 75.9 of IMA score. And so for IMC, the lower the score, the better it is. So for IMC, it has a lower score, so it is performing better. And for the other two scores, IMA score has better than any other model, and it is has a score of 78.8 on IMR. Now the key takeaway from here is it generalizes very well, and it maintains a strong performance without any additional training. And unlike supervised models, which may overfit to their level dataset, DINOv2 demonstrate robustness and transferability. So here are some more results on fine-grained feature. Here are some more results on uh, fine features on fine-grained benchmarks. So you can see various types of objects, scenes, and textures were used to evaluate the model. So food, C10, C100, sun, cars, aircrafts, VOCs, pets, flowers, etc. are used to evaluate the model generalization. So here you can see in most of the cases the model outperforms the SOTA models. So on image recognition or face recognition, it was tested on Oxford, Paris, Meta, and Amsterdam datasets. So you can see here we have also it outperforms in most of the cases. Now coming to results dissection. So on the Oxford dataset, it has an score 75 MAP score and 54 MAPH score, and iBot has 40 and 13, and OpenClick has 51 and 20. Paris, on the Paris datasets, its score the scores are 93 and 84, and on the Met dataset it has an 69, and the gap is 69. So the takeaway is DINOv2's version features dominate both state-of-the-art self-supervised and text-guided models on all four instant retrieval benchmarks, proving they work equally well at instant and category granularity. Now coming to semantic segmentation, here you can see it was tested on various datasets such as AD20K, cityscapes, and Pascal VOCs with frozen features, and in most of the cases it is outperforming the SOTA models. So the key takeaway is for semantic segmentation, DINOv2 features are plugged into mask to former and tested on AD20K, cityscapes, and Pascal VOC, and it outperforms most prior self-supervised models. And the key insight is that it indicates that DINOv2 captures fine-grained spatial features critical for pixel level tasks. Now for depth estimation, it was tested on NYU depth V2, Kitty, and Synergy VD, and mostly DINOv2 performs subpar with task-specific models, and the key takeaway is its self-supervised features can encode 3D structure even without ever being explicitly trained on depth. And these are the results of the depth estimation with frozen features. So here you can see it is almost equally subpar with the SOTA models. Now coming to qualitative results, uh, you can. So in this part, we'll explain the qualitative result. We will show the qualitative results reported in the paper, and this includes image retrievals, attention visualization, dense prediction, uh, and which helps us understanding the DINOv2's perceives and processes how it processes images. Now here you can see the visualization of the segmentation and depth estimation of these models. So in the first image you can see one input was taken from the AD20K dataset, and how the results are compared with the OpenClip G with the DINOv2G. And you can see the DINOv2 always outperforms in all of the cases. So here you can see the um, over the uh, depth estimation. Yeah, depth estimation is not good here. So the model is not performing well when estimating the depths of these objects in the images for the open clip, but the DINOv2 is performing well. And here also for segmentation, it has similar results, but it is with par with the SOTA models. So here you can see it segments the house very well, and here are some more results from the paper. So yeah, so these are the results from the open clip, and these are the results from DINOv2. Here visualization of the first PCA component. So you can see DINOv2 uh, very well extract the PCA features, PCA components. So key takeaway is that for instant retrieval, DINOv2 really shines on datasets like Oxford 5K, Paris 6K, and MMet, and it achieves state-of-the-art retrieval accuracy, surpassing the clip and supervised VITs. And the key insight is that DINOv2 is particularly strong at learning global and local patch similarities, which is key for retrieval. Now the result section. So summary of the findings of the results are that DINOv2 achieves state-of-the-art performance in many tasks, such as many tasks, often rivaling the supervised models, and its features are general, transferable, and robust, making it ideal for real-world applications. And applications so that careful data curation and training practices drive performance gains. Broader implication is that it shows it is now a practical alternative to supervised pre-training, especially in domains where labels are scarce, such as medical imaging, remote sensing, and robotics. And by releasing strong open source models, Meta AI has provided the community with a foundation that can reduce reliance on expensive supervised data.
Alright, so till now, authors have enhanced the existing self-supervised approaches, particularly focusing on discriminative methods, and demonstrate that with sufficiently large and curated datasets, such models can produce features surpassing those from weakly supervised or text-guided models. Now, let's look at how this model handles fairness and bias. You can see that the Dino version 2G model performs consistently higher than the Seer version 2 across all regions and income bands. However, if you look at the numbers for Africa and Europe, still a sharp drop, about 26 percentage points lower in Africa compared to Europe. Similarly, the model is about 32 points less accurate for low income homes than for the high income ones. Now, uh, this visual pattern shows that while this model is more fair than the previous models, it has still a bias towards rich images from rich and western countries. Now shifting to the people attribute test using the casual conversations dataset, look at here that almost all faces regarding regardless of gender, skin tone or age are tagged as human. That's the dominant color in the table. How now harmful labels like non-human or crime are almost never assigned. There's a small effect for men where the possibly human label appears more often, and that's because of the beard class in the data. But there's no clear harmful bias by gender, skin tone, or age. So the main takeaway is that curated self-supervised learning improves fairness, but as you can see, the regional and income gaps are still needed. Are still We still need more diverse and underrepresented images to fully close these gaps. Now, before moving on, let's look at this visual, figure 10, matching across images. This figure demonstrates that one of the strengths of this model's features. The lines connect semantically similar regions between different images, even when the objects or domains change. For example, the model can match the wing of a plane to a wing of a bird, or similar parts across photos and drawings. This ability to find meaningful correspondences despite changes in style or pose highlights how these models learn features generalize across domains. It is a qualitative sign that the model is learning more than just superficial patterns. It is capturing deeper visual semantics. Now let's look at the closer at the table 12, which breaks down geographical fairness and diversity. You can see that the accuracy numbers for this model and this year version 2 across different income buckets, low, medium, high. Now notice that the Dino versions 2 numbers are higher in every column, but pay attention to the gap, 67.4% accuracy for low income and jumping to 90.5% for high income. That's a 32-point gap we mentioned earlier. On the right, uh, table shows that table showing performance by region. Again, this model outperforms this year version 2 everywhere, but the gap between Africa and Europe is still clear. So this table reinforces that while this model is a step forward, still there's a strong western wealth tilt in its predictions. Now let's look at the table 14, which summarizes how the model assigns labels across gender, skin tone, and age groups. Look at the human row for this model. Almost all values are above 84%, and most are above 90%. The non-human and crime rows are essentially zero except for a tiny blip for male darker, and that's the 0.2%. The possibly human label is more frequent for males, especially those with darker skin, which, as mentioned, is due to the presence of a beard class. So the visual, so this confirms that this model assigns human labels consistently across demographics with no systematic harmful bias detected in this evaluation. Now let's talk about the environmental impact of training these models. If you uh, This model requires about 22,000 GPU hours, which translates to roughly 3.7 tons of carbon dioxide emissions. That's based on US grid averages and a PUE of 1.1. If you compare this to a text image model like Clip, which needs a text encoder as well, the emissions are about 10 times higher for the same size model. That's a huge difference, and you can see it in this table. Here it mentions the GPU hours for this model and it compares. Yeah, now the total emissions for the whole Dino version 2 project, including repeats and ablations, are kept under 1000 tons of carbon dioxide emissions. One important note visible in the table is that these numbers are only count GPU electricity usage. They don't include carbon cost of manufacturing or disposing of the hardware. So the takeaway here is that visual only models, self-supervised approaches, for visual only models, self-supervised approaches like this model are much more carbon efficient than the text guided ones.
To wrap up, DINOv2 represents a major leap in self supervised learning for vision. It closes the gap with supervised models by delivering frozen features that match or even beat those with weakly supervised methods like CLIP on a wide range of tasks, including classification, segmentation, depth, and instance retrieval. So, why does it work? There are a few key ingredients. First, an improved training recipe with a better regularization and loss design. Second, scaling up to a massive VITG backbone with a billion parameters. Third, using a carefully curated dataset of 142 million images which brings diversity without noise. And finally, distilling this large model into smaller, more efficient versions like VITS, B, and L so that the power is transferred in a reusable and efficient form. One of the most exciting things is the emergent capabilities the models show. Without any labels or supervision, DINOv2 learns to recognize meaningful objects, parts, and spatial structure like identifying heads, wings, or wheels across very different styles and domains. This shows a deep semantic understanding encoded directly in the features. And perhaps most importantly, these models are plug and play. You don't need complex fine tuning. Just adding a simple linear classifier is enough to get state of the art performance. That tells us the features are already rich and informative, truly general purpose. In short, DOV2 proves that self supervision plus scale plus smart curation can create powerful, label free vision backbones ready for real world use. Thank you.